So for this question here, calculate the amount of heat needed to vaporize a 90.0 gram of C3 at 7OH. So you definitely, in order to go from the mass to the moles, you have to calculate the molar mass of C3 at 7OH, right? So if I calculate that, the molar mass that I have calculated for this compound here, it turned out to be 60.095 grams per mole. Okay, I need that because I need to convert the mass into moles first, and then I will be able to calculate the kilojoules. So I'm going to set it up. I'm going to set the mass that I'm going to start with is going to be 90.0 grams of the compound is going to be 1 mole of compound. We have figured that out is going to be equal to 60.0095 grams. And then we have the heat of vaporization. It says 1 mole is going to be equal to 39.9 kilojoules. So moles is going to be cancelled by grams is going to be cancelled by gram. You're going to multiply everything on the top, divide by everything in the bottom. You will get your answer in kilojoules. Okay. This is what we have discussed, that the deposition and the sublimation. These are two processes. What is sublimation that we are talking about? It's solid directly going into the gas form. Okay. Deposition is going back into the solid. Okay. Okay. So gas going back into, so this is sublimation, and that needs to be called as deposition, right? Opposite to the sublimation. Make sure that it's not going into the liquid in both ways. Okay, so when you look at the sublimation, what is the requirement of heat of sublimation going solid? And the example that I gave you is dry ice, carbon dioxide. When you put that under room temperature, it never goes into the liquid. It directly goes. It is the temperature requirement for this solid is so low that even at room temperature is going to go into the gas directly. Even lower temperatures than room temperature will go into the gas. So you have to keep it at a very, very low temperature. Carbon dioxide is solid at 80 degrees Celsius. Okay, so these are the energy requirements, and it tells you that if you have things going directly from solid to liquid, this is what we call fusion or melting. Like ice is going into the liquid water, we call it diffusion. Okay, melting is called fusion, so there's energy requirement for that. And from liquid to gas, there's another requirement of gas that we call heat of vaporization. You know it, you're pretty much familiar with it now. So then if you want to get the heat and the kinetics, energy kinetics of things or matter going from directly from solid to gas, if you have these two, you can get it indirectly. Heating and cooling curve that we were talking about, that if you heat stuff like you have ice, you bring it to the room temperature, it's going to start melting because it's gaining heat. This is called heating curve. And then it's eventually going to go, if you increase the temperature, it's going to go into the gaseous form of water. So this is the heating curve for water, where we started water at -10, it was all ice. And then we increase the temperature by putting it at the room temperature. So from -10, it's going to start melting. At 0 degrees Celsius is the temperature where all the solid is going to be converted into the liquid. 0 is not freezing, keep that in your mind. 0 is where it's all melted after some heat is gained, and it's all melted. So what you see here in these two curves, in this curve, you see different phases. This one phase that we see here is this linear fashion, that temperature is increasing here and heat is being absorbed. And then you see this point here where heat is still being absorbed, but there's no change in temperature. That happens, okay, in heating curves and cooling curves. And again, a lot of heat is absorbed by the sample, and then temperature change is obvious for that up to 100 degrees Celsius. And then again, there's a point where the liquid is converting into gas, and that after adding some amount of heat in it, all the liquid water is going to be converting into the gaseous water. But you must know that heat is being absorbed, but there is no change in the temperature. So when we look at the heat kinetics or the energy kinetics of the heating curves, what are the requirements? Then we can divide it into different phases where the temperature is changing. We can always use the heat equation, right? We can use the mass of the sample times the specific heat capacity times delta T. The change in temperature is the most prominent thing. So we can calculate Q with the heat of equation. So for this phase from -10 to 100 degrees Celsius, this is the change in temperature. We can plug that in here. We can get the specific capacity of ice from literature and what amount of ice we started with. We're going to get plug that in here, get the difference of these two values, initial and minus, for the temperature change. You should be able to calculate the Q. For this part, we can call it Q1. So that's going to be the Q1. Okay, in different steps. But what about this one? Because there's no temperature change here, so we cannot do this, but we need to get that amount of heat as well, which is being absorbed by the sample. So what scientists have done, they have devised another formula for these kind of heat, which we can call it heat QX1, where they just took the number of moles of the substance and multiply it by the literature value of heat, or because it's fusion, it's melting, so we need the heat of fusion from literature, and that will be applied. So this is how we can calculate it. Okay, so this part, we will get the QX1. For this part, we'll get the QX1. And again, the same way we did the Q1, we can do the Q2 for this part. This time, the change in temperature is going to be from 0 degrees Celsius, which is initial, to final 100 degrees Celsius here, right? So we can have the delta T from final is 100 degrees Celsius, and initially 0 degrees Celsius, which is 100 degrees Celsius time. Specific heat capacity this time will be used for liquid. And then the mass remains the same. We can calculate the Q2, right? So this is how we can calculate the Q2 here. Q2, and for this portion, again, we can calculate the QX2 by using the delta H of vaporization, because it's vaporization happening, they're not fusion at this time. And that will be available through the literature, number of moles of substance that you started with, you can already have it, calculate it for yourself. And then the last portion, if you go all the way to the end of the curve, you have to do the Q3 again here. Then at the end, Q1 plus QX1 plus Q2 plus QX2 plus Q3, whatever you have calculated for all of them is going to be equal to the total heat requirement for this heating process for the water. This is an example of the same kind of problem, but we are not going all the way to the top of the heating curve. The question says that starting with -10 degrees Celsius, with 250 grams of ice going all the way to 5 degrees Celsius. So it's going to be, if you look at this curve here, it's going to be somewhere ending somewhere here, just this portion of that. Okay, so what do we need? We need Q1 for that. And for this portion, we need QX1. And for this little portion here, we need Q2. So we need to use heat of vaporization, not heat of fusion, not vaporization. So the total, the Q total is going to be the heat of ice from -10 to 6 degrees to. So the first thing here, the first phase here is where it's going from -10 to 0. Then there is a linear phase, horizontal line, that where heat is being absorbed, but there's no change in temperature. So we're going to use this equation. This heat is going to be the heat of fusion. We'll get it from literature. And then again to Q1. Qx1 and then Q2, which is only from little portion 0 to make it clear, from the 0 to here. Okay. You need the specific heat capacity of ice and you need the specific heat capacity. So this is going to be used in this equation and this is going to be used in this equation. So do this and give me the answer in your next class and let me know what is the answer. Now the last part here is the phase diagram. So I'm going to end this video here, and in the next video, I'm going to make short videos for you guys, so it's easier for you to watch these. The next video, I'm going to talk about the phase diagram.